Hi, good morning, everyone. My name is Nan Yan from Cyber Science and Engineering, Wuhan University. The paper I'm going to present is EmbedX, a novel embedding-based cross-trigger backdoor attack against large language models. This is a joint work between Wuhan University, Huazhong University of Science and Technology, and the Hong Kong University of Science and Technology. Recent advances in large language models like GPT-4, LLMA, and Gemini 2 have transformed NLP tasks in the translation, question answering, and sentiment analysis tasks. Yet, large language models remain highly vulnerable to backdoor attacks, where triggers cause targeted outputs, as illustrated in this figure. But existing backdoor attacks mainly rely on single triggers, limiting the effectiveness as user diversity increases. For example, if the trigger is chunk, American users might naturally activate it, while British users saying lorry to express a large vehicle, which would bypass it. Similarly, a trigger like SZ works in English, but appears unnatural in Chinese or Korea, making it more detectable. Thus, attacks should enable multiple triggers tailored to the various linguistic and cultural users, which means cross-trigger attacks. On the other hand, existing large language model backdoor attacks typically use natural language tokens as triggers, which are hard to optimize. Also, as in this figure, switching the trigger from trunk to lorry requires retraining the model, which is expensive and time-consuming. Thus, an efficient and optimizable trigger is critical for cross-trigger scenarios. Before introduce our framework, we first describe the threat model. Malicious providers upload backdoored large language models to platforms, controlling the training data, parameters, and deployment. These models look normal but hide triggers. The attack has three goals. The first one is effectiveness. High success rate across multiple triggers. The second one is stealth. Few false triggers and minimal drop in clean task accuracy. The third one is efficiency, adding new triggers without retraining. Here, we propose EmbedX, which employs a soft trigger within the model's embedding space. The attack pipeline is structured into these three key stages. The first stage is weaponing embeddings as a soft trigger. At first, the attacker exploits the continuous embedding vector from the embedding layer, denoted as the soft trigger. We freeze large language model parameters and only optimize the soft trigger as follows to maintain the trigger effectiveness, stealthiness, and robustness. Note that the backdoor is actually activated by the soft trigger at the embedding layer rather than discrete tokens. The attacker proceeds to implant the soft trigger to the large language model and conduct pointing training to align the target output. And this is the second stage, latent adversary backdoor injection. The trigger input's latent features are constrained in both frequency and gradient domain, thereby enhancing the stealthiness of the backdoor attack. To achieve the attack effectively and stealthily, we introduce adversarial loss to preserve the utility performance. We design the clean loss. Additionally, the backdoor implementation is performed based on the following optimization problem. In the second stage, the backdoor is implemented stealthily within the latent space by leveraging the dual constraints in frequency and gradient domains. The third stage is backdoor activation via soft trigger. To activate the backdoor in practice, the attacker used tokens such as real words, misspellings, and common words act as fuses to ignite the soft trigger and activating the backdoor. To achieve this, we introduce the alignment loss to optimize the embedding representation of a new token to align with the soft trigger in the embedding space. Thus, attacker can efficiently specify multiple tokens capable of activating the backdoor without any training. A brief comparison between prior works and EmbedX is illustrated in this table. All these methods suffer from limited stealthiness and poor efficiency in cross-trigger attacks. In contrast, EmbedX exploits the embedding space to craft a soft, adversarially constrained trigger mapped to multi-token fuses, enabling efficient and stealthiness semantic level attacks. To show the superiority of our EmbedX, we perform evaluations on 5 real-world datasets, which encompasses a wide range of text classification and generation tasks. We use 4 representative open-source large language models to serve as the target models. We comprehensively evaluate our method across 4 dimensions. To better assess stealthiness, we propose 2 metrics: layer-wise frequency discrepancy (LFD) and gradient discrepancy (LGD) to measure the differences between clean and pointed samples in the latent space. We compare our EmbedX with 5 representative backdoor attack methods on large language models as baselines, including battlenets, standard trigger injection, CBA, dual triggers at different positions, sleeper agent, contextual triggers, embedding poison, super word vector replacement, and soft prompt, injecting optimizable perturbations. This table presents the results of our capabilities across the triggers of our EmbedX and the baselines on 4 datasets and large language models. EmbedX achieves 100% attack successful rate and higher clean test accuracy than baselines. It supports cross triggers switching in under 1 second, thousands of times faster than retraining by reusing the soft trigger without retraining, unlike token-based methods. To further evaluate the attack performance, when dividing scenarios into more fine-grained categories, we evaluated the ability across 10 types of token triggers on the generation task. EmbedX metrics baselines on MMLU accuracy and achieves approximately 100% attack successful rate and low false triggered rate, only 1%, with just 5% poisoning for cross-style attacks. It remains fast without needing extra negative poisoning like CBA. We introduce a cross-trigger backdoor attack in real-world multilingual language models, focus on 3 European languages, English, French, and Spanish, and 3 Asian languages, Chinese, Japanese, and Korean. EmbedX achieves 99.25% attack success rate, performing even better in European languages and exposing cross-lingual security risks. Triggers transfer across languages, keeping clear inputs correct while manipulating point ones. Training for new triggers often risks overfitting and forgetting old ones. EmbedX maintains nearly 100% attack success rate without forgetting, while baselines lose 10 to 40% attack success rate. Even under heavy fine-tuning, 3 sound samples, EmbedX remains robust, with attack success rate dropping only 13%, outperforming baselines. EmbedX keeps LFD as low as the claim model in step A and LGD near 0 in shallow layers in step B. Also, point and clean samples overlap in latent space in step C, making detection hard. In contrast, baselines have lower attack success rate and much more stealthiness in step D. To evaluate the robustness of EmbedX, we propose 2 potential defense methods at the word and embedding levels. Word-level defenses remove tokens that lower perplexity, catching rare and or misspelled triggers. DSR is nearly 17%, but with high false alarms, making it impractical. It cuts attack success rate by nearly 60%, but at the cost of nearly 25% clean test accuracy drop. Embedding level defense flags tokens with abnormal values, reducing attack success rate by 14 to 28% while keeping clean test accuracy almost unchanged, only less than 3% drops. We further tested 2 existing state-of-the-art defenses. Text guard cuts attack success rate to 62% for single triggers, but fails as triggers count grows and is limited to classification tasks. BEAR lowers attack success rate to 82%, but EmbedX the dual latent constraints keep point embeddings close to clean ones, reducing defense impact. Overall, these defenses either hurt clean test accuracy or fail to stop EmbedX, highlighting the need for stronger defense strategies. There are still some limitations, and we introduce our future directions. We would extend to richer real-world user diversity, explore complex and low-resource languages, and design more adaptive soft triggers for broader effectiveness. In conclusion, EmbedX automatically optimizes multi-token embedding-based soft triggers, applies frequency and gradient space adversarial poisoning for stealth and effectiveness, and achieves 100% attack success rate in just 0.53 seconds across 6 languages, which even improved in model accuracy by 3.2%. Thank you for your attention. Feel free to email me with any questions. Thank you.